I'm pleased to introduce Professor Gushu Li, Assistant Professor in the Department of Computer and Information Science at the University of Pennsylvania, where he leads the Penn Quantum Systems Lab. Professor Li will deliver our first presentation titled The Future of Quantum Technologies. His presentation will provide an accessible yet forward-looking overview of the quantum computing landscape and help us frame today's discussion. Gushu, the floor is yours, and you may share your screen. Thank you.
Thank you, Raluca. And let me start the screen sharing. Can you see my screen?
Yes, we do. Thank you.
Yes. Okay, great. Thank you for the opportunity to speak at the Federal Reserve Bank of Philadelphia. And today I'm going to give a quick overview of quantum computing, what it is, what it looks like now, and what it looks in the future, and some basic ideas in quantum, why it may work, and how you may want to try quantum computers by yourself today. Okay, let's start. The keyword, quantum, actually starts about 100 years ago when around 90s, people invented a series called quantum mechanics, trying to explain the behavior of very tiny particles or material or matters of the behavior of matters under that very small scale. So this is called the quantum revolution because their behavior is totally different from what we see in a daily classical world. And one unexpected outcome of quantum mechanics is that after dozens of years, people invented a device called transistor using the framework of quantum mechanics, and then this transistor is later improved and turned into MOSFET, and combining many MOSFET together, we can have integrated circuit, which constitutes the foundation of classical today's classical computing. And after another dozens of years, another group of physicists saying that your classical computer is good, it runs very faster and faster, but you're still not fully utilizing the power of our quantum mechanics. That is, your classical computer is still doing computation in the rule of classical mechanics, those Boolean algebra. But our question is, can you directly do computation using the law of quantum mechanics? And that actually kicks off the second quantum revolution. And when people start thinking about, how can we do computation directly using quantum mechanics? People just start to think about, first, what kind of applications we can use? We can use quantum computer to compute, to accelerate. And also on the hardware side, what kind of technologies we can use to physically implement a quantum computer. And one major milestone in the history of quantum computing is that back in 1994, a famous mathematician called Peter Shaw, you probably heard of that, he invented this Shaw's algorithm saying that, you will be able to factor a very large integer if you have a large scale quantum computer, and you will be able to factor this integer in polynomial time. For this problem, we don't yet have a classical algorithm that can efficiently factor an integer yet, so it is believed to be a hard problem, and which is a foundation of many today's widely deployed cryptography system. When you surfing on the internet, use your security sort of rely on this assumption, and quantum computer will break that. Okay, then after another 25 years. Back in 2019, Google announced that on their 15.3 superconducting qubit chip, they're able to do a specific computation called a superposition experiment or sampling from a random distribution. And this specific application is hard to do on classical computers, but you can do it on their their superconducting quantum chip in just a couple of seconds. It is maybe an arguable result because the classical sampling algorithm is often improving, and maybe it's not really superposition now. But this it is always a big milestone there. And now people are more looking to how can we really do some moving forward and do practical applications out of quantum computing. In terms of like a hardware development, like I have this figure summarizing the existing development of like quantum hardwares of different like qubit types from different companies and some academia labs, and you can see that before like 2016, when I before I started doing quantum back in 2016, there are just a very few qubits, and most of them are in like experimental physics labs. And people mostly focusing on superconducting at that time, but they're already like started to like try other technologies. And then when I did my PhD between 2017 and 2022, people have started to have like devices of larger scale of like dozens of qubits, and IBM also launches the cloud access to their superconducting hardware. And then starting my job at Penn, you can see that many companies have like a roadmap to saying that, okay, they're going to achieve like up to maybe 1 million physical qubits in their quantum computer system. And some of them have already have like hundreds qubits in one chip. But let's see if they're able to realize their roadmap in the next couple of years. So previously that about hardware. Now let's take a look what are the potential applications of quantum computing. Quantum computing is not theoretically it's general purpose, it's universal, but we may not want to use quantum computing to, for example, play video games or surf the internet. It's usually considered as an accelerator to some key applications, mostly around the scientific discovery side. For example, we may be able to use quantum computing to simulate molecules in the chemistry and boost the drug development, and also study the condensed matter physics, or to do high temperature superconductors, or solve some math problem or machine learning problems. And also we have applications in encryption and decryption, as I just said, for example, the short algorithm. And the computing technology stack is also something similar to classical computing, where it is not just the quantum chips. We need control hardwares to control the chip. We need programming languages to describe your quantum algorithm, and we need the compilers architectures to connect the high level application down to the lower physical execution. So at this stage, I would say that we are sort of similar to the stage where back in 1945, when ENIAC, the first electronic general purpose digital computer, was actually developed at University of Pennsylvania. And there's still a long way to go. Maybe we need to, I expect that we will see a lot of changes, but now we have some prototypes. And this figure have a nice summary of the ecosystem of quantum computing. As you can see, there are many big companies and small startups focusing on different aspects in this business. Some focus on provide users experience about, for example, developing applications that can directly benefit user needs, and also have develop new applications for quantum computing, and offer softwares that people can use to program quantum computers, and also hardware vendors which can directly develop QPUs. There are also companies to doing the peripheral hardware components. For example, in addition to QPU, you need control electronics to control your quantum processor unit, and this is something also we have people doing that. Now let's talk a little bit about the quantum computing. So in quantum computing, the basic information processing unit is called a qubit. In contrast, a classical bit is either a 0 or 1 exclusively. You cannot have both 0 and 1 at the same time. But for qubit, in addition to being 0 or 1, qubit can be a linear combination of 0 and 1. So basically, it is not living in the Fock space or just using Boolean algebra. It is actually it is a vector in using linear algebra. So, and you can use a vector to represent such a state. And generally, if you have if you have a qubit of more than 1 qubit, you will have a larger space. The rule to combining a two quantum system is that you take a tensor product of two different the vectors of two different systems. So if you have 2 qubits, you will have a state vector of 4 complex numbers. which is like a 4-dimensional unit vector. And if you have like a n qubits, you will have like a state vector of 2 to the power n complex numbers. Like in contrast, you can see that, okay, if you have just a classical bit, you will have like an n-bit string. But if you have n qubits, you're sort of encoding a very large number of like information in with like a 2 to the power n complex numbers in just like a n physical entities. So which is like a sort of like a quite compact encoding. Okay. And then one key aspects of like a quantum computing, which is very different from classical, is that, okay, when you measure the quantum state or a qubit, the like a measurement is very different from the real operation in classical computing. So suppose we have like a quantum state of like a linear combination of 0 and 1 with like this A and B as amplitude, and the measurement result will be probabilistic. That is, okay, you with probabilistic like a square, you will observe like a 0 outcome, and the state is changed to 0 after this measurement. And with probability b square, like you will be able to observe like a 1 outcome, and the state is changed to 1 state. So this is like a projection operation. Like you're projecting this like state vector into like 2 bases. So this is why we also call the measurement a projective measurement. And the key thing is that, okay, the state is usually changed after the measurement, which means like in measurement, we will lose information. So there's no like a simple read operation we can do like we deal with classical data. So there's one thing I want to emphasize is that, okay, quantum computing is not like doing all possible computations like at the same time and then measure the result. It's not possible because when you measure the a very large like a state vector, you will need a really a lot of samples if you do to recover the distribution. If you do not do any like intelligent like encoding or like algorithm design. So there is no like a straightforward like a benefit. You really need sophisticated algorithms to realize your advantage of quantum algorithms. And regarding the execution, I also want to highlight the difference between like classical and quantum. And in classical, usually like the data travels where like you have input, you do some operations on this data, and then you get the output, and you feed it into another like a functional module, and then you get the output, and then like you do it like in seriously. Okay. For quantum, like you can. There's one theorem called that. Okay, you cannot perfectly copy an unknown quantum state, which means, okay, you cannot duplicate quantum data easily. The way we do quantum computing is that we always have like a fixed like a set of like qubits encoding the information, and instead of like the data travels, we just put the operation onto this qubits. So that's a different model of execution comparing like quantum and classical. And in terms of like maybe one of the most interesting application of quantum computing related to finance is cryptography. And I want to use this example of short algorithm to give a quick understanding of why quantum computer can be faster than classical computer. So in short algorithm, the key question is that we want to factor a large integer like n equals to p times q. Okay. In classical computer, it is very hard to do so because you basically need to do some iterations to try different like factors and see if n can be factored by this number. But in quantum computer, do this problem in a totally different way. So instead of directly factor the larger number n, a quantum computer can detect the period of this specific function that fx equals to a to the power of x modulo n. And this is already also like a hard in classical computing, but in quantum computing, you can do this quite efficiently using a specific version of like a Fourier transform, which is called a quantum Fourier transform. Okay. After you do this quantum Fourier transform, you will see a bunch of like spikes representing the period of this of this function here, and then you will be measure this period with high probability, and actually then you can like directly find the factors of using this period, okay, by some like a number theory. So in summary, like quantum computing, like it is not very good at like directly doing some operations on some specific data. Instead, it can very goodly like analyze the correlations or relationships between a large data set instead without like touching the individual data. Okay, this is some like a unique advantage of quantum computing that is hard to implement in classical. And now let's talk about some like hardware basics. So how do we really implement the hardware? So I would start with this example from superconducting chip, like pursued by both like Google's and IBM. And this is like an example figure of IBM's like a 5-qubit chip. You can see that, okay, they use kind of this like a dark squares here as this like basic building blocks like this to represent to encode a physical qubit. And the basic like idea here is that, okay, if we have like a resonant oscillator, like you will have if you lower it to very low temperature, you will have like some like discrete energy levels. And by adding some nonlinearity here, you will be able to have some like a non-equally like divided energy levels, and then you will be like using the lowest two energy levels as the basis state of 0 and 1 to encode quantum information. And also like in terms of the in between these physical qubits, you will have like some wires as resonators to connect the physical qubits to do like a multi-qubit logical operations. And there's one slide I just added this morning. If you have already heard that, like this year's Nobel Prize in Physics was awarded to like John Clark, Michel Devaux, and John Martinez. These three guys published a paper like 40 years ago, invented the technology of like this technology is directly it's basically the prototype of like this superconducting qubit. So this is like why this year's Nobel Prize is highly related to quantum computing. Okay, and to control this superconducting qubits, you need like some very special operations. Instead of like in Boolean algebra in classical bit, just flip the bit, you do and you do or. Like quantum computing are analog. So basically, to control like this chips, you need to convert a quantum program into some analog control signals, sending them into different ports of this chip to like execute the logical operations you want to execute. And in addition to superconducting, there are also other technologies actually actively like being pursued by like different hardwares. By different vendors. For example, we have trapped ions, which are you probably heard of like IonQ and Quantinuum. Those are like two star startups for trapped ion quantum computing. And in this technology, like you encode the quantum information in the internal energy levels of an ion. And you use like electronic and magnetic field to trap ions in some specific locations and then do controls using lasers. And there are also like promising technologies like a neutral atom, where like you constrain some neutral atoms in a space using lights, and then you apply like different lasers to like excite and the neutral atoms to computation. And there are also like photonics-based quantum computing using like the state of photons to computation, and also like there are quantum dot devices using the spin up and spin down of electrons to quantum computation. Like those are many. There are like a couple. These are just a couple of like different technologies actively being pursued by different people. And in terms of today, like quantum computers is not really it's not far away from yourself, from you. Actually, you can access to quantum computers by just using your laptop from your home, from your like office. You can just log into this website, IBM Quantum, and like register account, and we will have basically have some free access to their hardware every month, and you can try some simple circuits. And you need to using their software to program and do some computation, do some simulation. And they have this IBM have this very nice circuit composer, which is legacy function. You can directly draw quantum gates to compose a quantum program, and you will be able to see the probability of measuring different outputs here. And here is a list of IBM devices you can pay to access. I don't think they are very cheap, but if you are doing research, you should be able to try that, because doing experimenting in real devices is always different from doing things on simulators. Okay, I guess that's pretty much I want to introduce today. Thank you again for the invitation, and I'm happy to take some questions.
Maybe I can ask you about an issue that I keep hearing, which is the issue of error correction. Do you have any thoughts on that?
You asked about like the error corrections, right?
Yeah.
Okay, so for error correction, there's always a debate like whether we need error correction to like really deliver the advantage of quantum computing. Some people like IBM, they try both things. For example, IBM have this like a quantum utility program trying to see if they can have some like early applications of quantum computing without using error correction. They are trying to do especially the material science simulations, which can some applications that can naturally fit on their device. That's one direction. The other direction is that we just do error correction to do large scale fault tolerant quantum computing, and I think both of them are important. And I must say that error correction is now one of the most important research topic in this area. Like many people and the companies are working in this direction, trying to see if we can push forward the frontier. Yeah.
There is a question on the chat about a simulation of quantum computers available based on classic computers.
Yes. I think there are many of them. For example, in IBM's Qiskit, there's a simulator called AER, and you can simulate I think up to a little bit above 20 qubits on your laptop. So basically, the complexity is exponentially large to the number of qubits. You can simulate probably 20 to 25 qubits on your laptop, maybe 30 qubits. And then for 40 qubits, you probably need a supercomputer to do the simulation. And going beyond that, things is sort of becoming classically intractable. But there are also other approaches to do classical simulation using some specific algorithms to some specific quantum programs. Yes.